This is part 1 of the trig functions videos. We're going to start off reviewing right triangle trigonometry from geometry class. So we'll look at properties of similar triangles, regular trig ratios, inverse trig ratios, and then do a couple examples. So what we start off with when we learn about trig in geometry is just looking at a line that's been graphed on a regular coordinate plane. So we can find the slope of this line by drawing a slope triangle, which shows us the change in x and the change in y of our line between any 2 points. And we know that no matter how big or small we draw that slope triangle, the ratio of change in y to change in x is always going to give us the same slope, which makes sense because the line has a constant rate of change. It has the same slope no matter which 2 points you're going in between. So if I call this change in x1 and change in y1, change in x2 and change in y2, I know that change in y1 over change in x1 is equal to change in y2 over change in x2. So those ratios are equivalent. They're the same value. If, however, I changed the angle that my line was crossing the horizontal at, so if I made it steeper or less steep, that would change the ratio of change in y to change in x. So what we end up having are a series of similar triangles because both of these triangles have right angles and they cross the horizontal at the same angle. So they have the same, what I'll call theta for these videos, the same slope angle. So these two triangles are similar by angle-angle similarity. And then that's another reason that it makes sense that the ratio of rise to run in both triangles is the same, because we know that ratios of corresponding sides in similar triangles are equivalent. Something that might seem a little trivial is that if I took my slope triangle, which I just have here as a little movable triangle, and I rotated it, and I could rotate it as much as I wanted, the ratio of change in y to change in x would always be the same. So if I take this triangle and I make a copy and I rotate it, if I call this y and this x, when I rotate my triangle, this will still be y and this will still be x. And so as long as these are both right triangles, the ratio of y to x will be the same even if it's rotated, because rotations are rigid transformations. So the way that this all comes together for right triangle trigonometry is that we are only able to use our trig tools when we have a right triangle, which is why it's called right triangle trig. And without that right angle, you don't have the angle-angle similarity. So the conclusions that we made over the last couple slides don't hold true. So we just came to realize that for a given slope angle, the ratio of change in y over change in x is always the same no matter how big or small the triangle is. Because we are always using right triangles, if we say that one of the other angles is the same, then we're saying that we have angle-angle similarity. So we have a name for that ratio. Instead of calling it slope, we're going to call it the tangent ratio. So the tangent of theta equals what I've called change in y over change in x. But we have right triangles that aren't explicitly slope triangles. So what I really want to notice is that change in y is always across the triangle from theta. It's not the hypotenuse, it's the leg that's across from theta, and change in x is always next to theta. So we call these opposite and adjacent. And so one way that I can write the tangent ratio a different way is to say that tangent of theta equals opposite over adjacent. And that's the first trig ratio that we learn about in geometry. One last way of thinking about that tangent ratio is that the tangent of theta is the height of a right triangle when the base is 1. So if we lock that adjacent leg to be equal to 1, then this opposite leg equals the tangent of theta, depending on what that angle is. So we can say the tangent of theta over 1 equals opposite over adjacent, and all we're doing is setting up a ratio between similar triangles. So there are two other trig ratios that we learn about at this time. So if this is my right triangle with an acute angle of theta, my opposite leg is the one across from theta, my adjacent leg is the leg next to theta, and my hypotenuse is the side across from the 90-degree angle. That's the longest side in the right triangle. So we've got that the tangent of theta over 1 is equal to opposite over adjacent. And the other two ratios that we learn about are the sine of theta over 1 equals opposite over hypotenuse, and the cosine of theta over 1 equals adjacent over hypotenuse. So if I'm looking at a triangle that has a right angle and an acute angle of 28 degrees, and let's say I know the hypotenuse is 6, and I'm looking for the height, or the opposite side length. So I'm looking for the opposite and I know the hypotenuse, so I'm going to use the sine function. So I can set up the ratio, the sine of 28 over 1 equals opposite, which is x, over hypotenuse, which is 6. So we want to start by thinking about why this equation makes sense. Just looking at the left side of the equation, we've got the sine of 28 over 1. And I need to really understand what that means for a moment. So if I was taking my calculator and using the sine function on my calculator, I'm going to look at that as if it's a function machine for a moment. So I'm inputting 28 to my calculator because I'm typing in the sine of 28, and my output is going to be 0.47. So what this means is that if I had a triangle that had one right angle and an acute angle of 28 degrees and a hypotenuse of 1, my height, or my opposite leg, would be 0.47. And if I want to go from this right triangle to the right triangle in my problem, I need to dilate it by a scale factor of 6 so that the hypotenuse becomes 6, and then the opposite leg would also get multiplied by 6. And so as I solve this equation on the left, I need to multiply by 6 on both sides to get x alone. So I end up with x equals 6 times the sine of 28, which is 6 times 0.47, which is 2.82 units. So the process where I'm solving algebraically and the process where I'm creating similar triangles and dilating gives us the same answer, and it connects the math, so it really makes the equation have a context, makes it make sense. The last thing we want to look at before we do some more examples is inverse trig. So if I have my right triangle and my theta as one of my acute angles, here's hypotenuse, opposite, and adjacent. And I'm going to use my little function machine again. I'll use cosine this time. So when I input something to the cosine function, it's an angle, so it's my theta. And what my calculator or Desmos spits out is the ratio of adjacent to hypotenuse for that given acute angle. So if I have my two side lengths, adjacent and hypotenuse, but I'm not sure what my angle is. I need to use this function machine in reverse. So I need to have an inverse cosine machine that allows me to input my ratio of adjacent over hypotenuse and outputs my theta. So an example of this would be a right triangle where we're trying to find theta, and we know the hypotenuse is 15 and the adjacent side is 4. So I could set up the equation cosine of theta equals 4 over 15, and my unknown here is the theta. It's involved in that function, cosine of theta, so I need to use cosine inverse of 4/15 to get out theta, and I would use a calculator to do that. So in this particular case, theta equals 74.5 degrees. So this first example has a hypotenuse length of 20 and an acute angle of 15 degrees. It is a right triangle, so we can use our trig tools. And we are looking for both the length of the adjacent leg, which is labeled M, and the length of the opposite leg, which is labeled N. So I'm going to start by setting up a cosine ratio. The cosine of 15 over 1 is equal to the adjacent leg, which is M, over the hypotenuse, which is 20. And I want to solve for M, so I need to multiply by 20 on both sides. Geometrically, this makes sense because the cosine of 15 is the length of the adjacent leg when the hypotenuse is a length of 1, and we need to multiply that length by 20 to dilate our triangle to be the same size as in our diagram. So now I've got 20 times the cosine of 15 equals M, and because I've written an equation that's solved for my variable, I can go ahead and plug that into a calculator. So 20 times the cosine of 15 equals 19.32. So M equals 19.32. And to find N, I can use the Pythagorean theorem now that I know 2 out of 3 leg lengths of a right triangle, or I can use a different trig ratio. Because I have the adjacent and the hypotenuse, I can use the sine ratio or the tangent ratio. I will use the sine ratio. So sine of 15 over 1 equals opposite, which is N, over hypotenuse, which is 20. So N equals 20 times the sine of 15, because I had to multiply by 20 on both sides to get N by itself. And 20 times the sine of 15 is 5.18. So I've got all the missing sides of my triangle. I could use the Pythagorean theorem to verify that when I do 19.32 squared plus 5.18 squared, I get 20 squared. So my next example has a right triangle with an acute angle of 43 degrees, an opposite side length of 5, and an adjacent side length of x. So I've got opposite here, adjacent over here, so I'm going to set up a tangent ratio. The tangent of 43 degrees over 1 equals opposite, which is 5, over adjacent, which is x. And here my unknown that I'm solving for, my variable, is in the denominator. So to get that out of the denominator, I need to multiply by x over 1 on both sides. So I get x times the tangent of 43 equals 5. And now to undo the multiplication by the tangent of 43, I'm going to divide by the tangent of 43 on both sides. So my equation becomes x equals 5 divided by the tangent of 43. That on the left side here, this tangent of 43 over tangent of 43 is a giant 1, so that gets canceled out. Now that I've got my variable solved for, so it says x equals, I can use my calculator or Desmos to evaluate that expression. So 5 divided by the tangent of 43 is equivalent to 5.36. So if I have an acute angle of 43 degrees, when my opposite side length is 5, my adjacent side length is 5.36, those leg lengths are really similar, and that actually makes sense because if my acute angle were 45 degrees, my opposite and adjacent sides would be equal because I would have half of a square. So if I have an acute angle of 45 degrees, my leg lengths are equivalent. So that's just one way that we can check to make sure that our answers are correct by thinking about what the triangle would look like if it were drawn to scale. And I'll do one example with inverse trig. So if I have a right triangle with an unknown acute angle, opposite side length of 4, hypotenuse side length of 15, I can set up a sine ratio. The sine of theta equals opposite, which is 4, over hypotenuse, which is 15. Here my unknown variable that I'm trying to solve for is theta, and it's inside of that sine function. So what I need to do is use an inverse sine function so that instead of inputting an angle and getting out a ratio, I'm going to input a ratio of opposite to hypotenuse, and my function will spit out my angle measure. So I'm using an inverse function, which switches the inputs and the outputs. So with that one move, I've solved for my unknown variable, and so I can use inverse trig, sine inverse of 4 divided by 15, and I get that theta equals 15.46 degrees. A small note about how to use inverse trig functions on your calculator. If you are using a graphing calculator, you want to hit the second button, and then you can hit sine, cosine, or tangent. You'll see that sine inverse is written in small letters above those buttons. If you're using Desmos, you go into the functions button, and trig is that first tab, and arc sine is the same as sine to the -1. So arc sine is the mathematical notation that is the same as sine inverse on our graphing calculators. Alright, so make sure that you are completing some practice problems and check in with your teacher when you need to take a retake.